Next, we're going to discuss a couple of applications to our main theorem, which we will write as corollaries. But first, let me introduce the definition which we'll use in our first corollary. Let G be a polynomial over a ring in m variables. A0x of G is called simple if at least one of the partial derivatives of G is non-zero at x. As a quick example, G of x1, x2 equal to x1 minus a1 plus x2 minus a2 squared has a root a1, a2. a1 and a2 are both in R. And if you look at the partial derivatives, dg by dx1, this is equal to 1, and dg by dx2, this is equal to 2 times x2 minus a2. By the usual convention, a ring contains a multiplicative identity denoted by 1, and that 1 is not equal to 0. So this root is simple. And as a non-example, if you look at g1 of x1, x2 equal to x1 minus a1 times x2 minus a2, if you look at this, it also has a root a1, a2, but if you look at the partial derivatives, they both vanish at a1, a2. So this root is not a simple root for this second G. Now we can state our first corollary. Let f be a polynomial in m variables over Zp, and consider its reduction modulo p. Then every simple zero of f modulo p leads to a zero of f with coefficient in Zp. The proof is easy in view of theorem 1. We set n in theorem 1 to be 1 and k to be 0. And therefore n minus k is equal to 1 in theorem 1. If little x is a simple root for f modulo p, then by definition there exists a j from 1 up to m such that df by dxj is not congruent to 0 modulo p. At this little x. And this condition implies that p does not divide df by dxj. So if we view this partial derivative df by dxj as an element in Zp, then this is invertible by proposition 2 on page 12 of Sarah's book. And because it is invertible, the p-adic valuation of this guy must be equal to 0. because its p-adic factorization is just itself. Now by theorem 1, we can conclude that there exists a zero y of this f over zp. Namely, f of y is equal to 0 in zp, such that now n minus k is equal to 1, so the conclusion corresponds to y is congruent to x modulo p. And this finishes the proof of the first corollary. Our next two corollaries are related to our favorite polynomials, namely quadratic forms. Corollary 2 states that if p is a prime number not equal to 2, and let f be a symmetric quadratic form with coefficients in zp, whose discriminant, namely the determinant of the matrix formed by aij's, is invertible. And we know this condition is equivalent to saying that P does not divide the determinant of the matrix formed by A sub ij's. Now let A be an element in ZP. Then every primitive solution of the equation f of x congruent to A modulo P lifts to a true solution in ZP. Here, what do we mean by a primitive solution? What we mean is that this is the old definition, so let me recall it. x1 up to xm as a vector in ZPM is called primitive if at least one of them is invertible, namely not divisible by p. This is the definition for the primitivity here. And now let's prove this. Now, in view of our corollary number 1, it suffices to establish that every primitive solution to this equation is simple. Namely, that solution does not annihilate all the partial derivatives of f, which is the definition of simplicity of roots. Actually, the constant element a here is not important, because when we take the partial derivative, a always vanishes. So in view of corollary 1, it suffices to look at just the partial derivatives for f and show that the root here will not annihilate all the partial derivatives for f. Now let us prove this by contradiction. Suppose there is a primitive solution that is not simple. Namely, that root will annihilate all partial derivatives modulo p. What does that mean? That means df by dxi and the root is indeed congruent to 0 modulo p for all I from 1 to m. Now, what is the partial derivative of f by xi? It is easy to check that this partial derivative is 2 times the sum of a sub ij's times xj for j equal to 1 to m congruent to 0 modulo p. For all I from 1 to m. And now, because 2 is not equal to p does not divide 2. So 2 is invertible in z mod pz. Therefore, we can cancel this 2 from both sides. This is because p is not equal to 2. So 2 is invertible in z mod pz. So now we are trying to solve this system of linear equations in z mod pz. And we look at the hypothesis in this corollary. We'll immediately see this will lead to a contradiction. Because if you write this in the matrix form, then by our assumption, the discriminant, namely this determinant, the determinant of this matrix, is invertible in Zp. But being invertible in Zp means p does not divide this determinant, which means in z mod pz it is non-zero. And we look at this vector x1 through xm. We assume that this is a primitive solution. That means at least one of x1 through xm is invertible, i.e. not divisible by p. So over z mod pz, this is a non-zero vector. So we have that in the field z mod pz, the finite field's p elements, there is a matrix with non-zero determinant multiplied to a non-zero vector. And this product cannot be equal to 0 in the field z mod pz. So we have a contradiction to this basic linear algebraic fact. And this finishes the proof of corollary number 2. This is a case when the prime number p is not equal to 2. Our last corollary deals with the case when p is equal to 2. Suppose p is equal to 2 and f be a quadratic form that is symmetric with coefficient in Z2, and let A be an element in Z2. Now let little x be a primitive solution of f of x equal to A modulo 8. Now, the corollary number 3 states that we can lift this x to a true solution of f equal to A in Zp, which is now Z2, provided that x does not annihilate all the partial derivatives of f modulo 4. And this last condition is fulfilled if the determinant of the matrix formed by A sub ij's is invertible. The proof of this corollary uses theorem 1, the main theorem of this section, in page 14 of Sayre's book. To use our main theorem, we set n equal to 3 and k equal to 1. And n minus k is equal to 2. And now you can see where those 4 and 8 come from. This 4 is equal to p to the n minus k in this case. And 8 is equal to p to the power n in this case, because n is equal to 3 and k is equal to 1. Now to use our theorem 1, it suffices to establish that for some j, the periodic valuation of df by dxj at x is equal to k. For some x, that is the root of f modulo p to the power n. And in view of our assumption here, let little x be a primitive solution of f of x congruent to a modulo 8 that does not annihilate some df by dxi. Now it suffices to show that df by dxi evaluated at x has periodic valuation equal to k, which is 1 in our case. To show this, we first observe that trivially this guy is always congruent to 0 mod 2. And this implies that this partial derivative has periodic valuation when p is equal to 2, at least 1, because it can always factor out at least 1, 2. So to show that periodic valuation is precisely equal to 1, it suffices to establish that 2 squared, which is 4, does not divide df by dxi at this little x. And that is exactly what this condition talks about. So 2 divides this, but 2 squared with 4 does not divide it. And this implies that the periodic valuation, which is 2-adic valuation of this partial derivative, is equal to 1. And therefore, by theorem 1, this x indeed leads to a true solution in Z2. Now it suffices to check the last sentence in corollary 3. Why this last condition is fulfilled if the determinant of the matrix formed by A sub ij's is invertible in Z2. So let's check this. To check the last statement, we observe that this condition, that the power derivative is not congruent to 0 mod 4 is equivalent to when we cancel 2 from both sides and replace mod 4 by mod 2. This equivalence follows from the following fact. For z in Zp, p times z is congruent to 0 mod p squared if and only if z is congruent to 0 mod p. This is easy to check. The backward direction is trivial because this condition means p divides z. So p squared will divide p times z trivially. The forward direction is also easy. If p times z is congruent to 0 modulo p squared, then by p-adic factorization, we have this guy equal to p squared times some z prime for some z prime in Zp. But this equation, as an equation in Zp, will allow us to cancel p from both sides. This is by the injectivity of the multiplication by p map. So we can cancel a p from both sides. And this implies that p divides z. So this guy, not congruent to 0 modulo 4, is equivalent to saying that this guy is not congruent to 0 modulo 2. And for the last equation, we're going to use the same argument as in the end of corollary 2's proof. We look at this linear system formed by this matrix with a sub ij's. I should make those xj's smaller. And now because x1 through xm form a vector that is primitive. So in particular, this is a non-zero vector in the field z mod pz, which is z mod 2z in this case. So the product of this matrix with this vector being non-zero modulo 2 is implied by the condition that the determinant of this is non-zero modulo 2, i.e. this determinant is invertible in the ring of p-adic integers z2. And this finally finished the proof of corollary number 3.